In the last video, we saw a method that we can use to simplify many proofs or to deal with some arguments where standard proofs are really not a possibility, that of a conditional proof. In this video, we're going to look at another method of constructing a proof called an indirect proof. Now, an indirect proof can be used in a number of different ways, but it can be used to derive either the conclusion of an argument or an intermediate line in the proof of some other sequence. And the technique starts here by assuming the negation of the statement to be derived, and then deriving a contradiction on a subsequent line in the proof. And so the indirect proof sequence is then discharged by negating the assumed statement. We will see examples soon enough that will hopefully make sense of the whole process for you, but the reasoning behind this procedure is fairly straightforward. If in the context of a proof, the negation of a statement leads to an absurdity, that is to a contradiction, then we have indirectly established the truth of the original statement. That is why indeed the procedure is sometimes called a reductio ad absurdum, which just means reducing to the absurd. The indirect proof method needs to be displayed in a special way to distinguish its role in the proof. And the way in which we'll do this is quite similar to that of a conditional proof, in that in our indirect proof, the sequence starts with an assumption, and then we will indent the proof and everything that follows from that assumption. So let's jump into an example of how this is supposed to work so we can see what you do when you construct an indirect proof. In this particular argument, our first premise says, if not M, then not N. The second premise says, if not L and not M, then N. And then the conclusion says it's either L or it is M. Now, the first step in all of this is rather naturally to just set up the proof like we always do, listing your premises and then setting your conclusion off to the right, where we can start to label all of our justifications. Now notice that the first step in constructing an indirect proof is to begin by assuming the negation of some particular statement. In this case, we're going to look at this conclusion. It's either L or it's M, and then we want to negate the entire thing. And notice what we're doing here is we're going to assume, for the sake of the proof, that the negation of this conclusion is true, and then place it here as merely an assumption. Note too that the line is going to be indented because it is justified only as an assumption. And this means that whatever we might derive logically from the statement can only be used in this indirect proof. Now the justification of this is going to be labeled simply AIP, which of course stands for assumed and an indirect proof. So let me jump ahead a bit to try to explain to you exactly what the goal you're aiming at in constructing your indirect proof might be. The goal of an indirect proof is to see if you can produce a contradiction using valid inference drawn from this assumed claim at the beginning. In this particular instance, notice what we're aiming at will end up being in and not in, which is clearly contradictory. And so if I can, working from this original negated statement, figure out a way to produce a contradiction from it, what we find is that we can now say with certainty that this negated claim cannot be true. And this by default will show us that the original proposition itself must be true. Now, where exactly you ought to be heading when you start an indirect proof is not always clear, and it's not always easy to determine. But if you look at this particular argument for a while, the idea that we might want to put together in with not in into a contradiction pretty much suggests itself, since both of these terms are given as the consequent of some sort of conditional statement. And so we start our indirect proof again with the negation of some statement, in this case, the particular conclusion, it's either L or M. And when we write our justification, what we want to write is simply AIP. And of course, this simply stands for assumed in an indirect proof. Now, a fairly reasonable starting place with all of this is to take line 3 and simply convert it using De Morgan's law into a conjunction of it's not L and it's not M. And you can see why, if you just start looking around in the argument, that particular statement is the entire antecedent of line 2, which is simply a conditional statement. And remember, our goal in some sense is to derive or pull out in as a statement of its own, so I can put it together into this contradiction. And so on line 5, we can now say in is true based on the rules of modus ponens using line 2 and line 4. So with line 5, I've gotten half of the contradiction I'm aiming at. I have in, and now I need to figure out how to pull out not in from line 1. And rather clearly, since it is a conditional statement, I'm going to need to use modus ponens to get there. And so what I need to do is somehow affirm the antecedent of line 1. And rather clearly, I can find not im where I need it in line 4. And so I need to find a way to get im, or not im, out of this particular line. And of course, that is rather easily accomplished by using the rule of simplification. So in line 4, which says it's not L and it's not im, I can simply pull not im out of it and place it on its own in line 6 as a true proposition, or assumed to be true proposition, not im. And this allows us to pull out the not in that I was aiming at in this whole time. Using the rule of modus ponens with line 1 and line 6, I can now say that I know not in is true. And of course, this puts us in a rather good position to state our contradiction, because I can now use the rule of conjunction to put together line 5, which simply says in is true, with line 7, which says not in is true, to make the claim that both in and not in must be true. So what exactly does all of this accomplish for us? Well, it turns out that if this original assumption here, using valid inferences step by step by step, leads us to draw an absurd conclusion, that is, it leads us to this contradiction, then we're in a position to conclude from this that the assumption must be wrong. And so at the end of the proof, we are able to discharge the indirect proof sequence by negating that original assumption that was negated. In this case, we can essentially negate the line 3 and discharge the proof sequence with the claim that it is not the case that not L and M is the case. And this is, of course, the final result that we're after. Because at this point, we can simply take line 9, which is a double negation, and then apply the rule double negation to it to produce exactly the conclusion that we started with, which is simply it's either L or it's M. And of course, what that does for us is show that this is in fact a valid argument, just like all these proofs are supposed to be doing. Now, it's very important to remember that just like with a conditional proof, we cannot use any line within an indirect proof sequence outside of that sequence as part of our overall proof, because everything there is working based on a mere assumption. But what this does do for us is give us evidence for the claim that will ultimately be made in line 9. But of course, once we're able to discharge that statement from the indirect proof, it becomes part of the original proof and it is determined to be true. So we know that that's a true statement, and now we can use it in our proof just like we've been doing. Now, before continuing, we might stop and think about this issue for a moment and wonder what's really wrong with the contradiction in the first place. The issue really amounts to this. It turns out that pretty much anything will follow from a contradiction. And that suggests that when we prove something by way of a contradiction, it turns out it's pretty much useless. If, for example, I want to prove to you that some claim X is true, a contradiction can do this, but it can, at the same time and using pretty much the same logic, also prove it's not true. And so a proof from a contradiction fails to give us any coherent reason to accept any claim as true. Let me show you what I mean by way of some very simple and simplistic examples. If we look at this particular argument, it says P is true and not P is true are the two premises, and the conclusion I want to draw is Q from this. Now, if my goal here is to prove Q, I of course have to provide that by adding it into the equation using the rule of addition. And so I can simply say on line 3 that it's either P or it is Q. And then, of course, I can draw the conclusion that Q is correct by simply using the rule of a disjunctive syllogism, taking line 3 and then the negation of P in line 2 to draw that particular conclusion. So notice what I've done there is I've proved to you using this contradiction, essentially P and not P, that Q has to be true. But notice I can use the exact same evidence, the exact same premises that I have in the first example to prove exactly the opposite claim that Q is not true. And the reasoning here is pretty much the same thing. The next step is to simply bring Q into the mix by way of addition, so I get it's either P or it is not Q. And of course, I can now prove that not Q is the case very simply by appealing to a disjunctive syllogism. Now notice what this shows us. The problem here, as illustrated by these two different proofs, is that you can derive anything you want from a contradiction. And so when you prove something using a contradiction, it just doesn't really do any work for us. It doesn't establish anything or give us good reasons to think that something might be true. However, as we have seen in the indirect proof, this fact can be turned to our advantage. Whenever a set of statements implies a contradiction, then what this means is we know that not all of these statements can be true. So the method of indirect proof allows us to show the following claim. If a set of premises are assumed to be true, and the negation of the conclusion leads to a contradiction, then it follows and follows necessarily that the negation of the conclusion must be false based on the original assumption of the claim. And of course, if the negation of the conclusion must be false, then the original conclusion must be true. This, in a nutshell, is the logic behind an indirect proof. So let's walk through another example here. And I would like to suggest to you that as I go through these in the video, it doesn't hurt to pause between steps in the logic there so that you make sure you understand why some particular move has been made. So here's a fairly straightforward argument. Our first premise says if D is true, then C is true. The second premise says it's either A or it is B and C. The third premise says if A is true, then D is true, and then we conclude that C is true. So the first step is to simply set it up like you always would into a proof. And of course, if we want to use an indirect proof here as a method for seeing if this is valid or invalid, the first step is to take the conclusion there and simply negate it and place that as an assumption on the next line, which is line 4 here. And again, notice it needs to be indented so that we recognize we're dealing with an assumption here. And then we want to write as our justification simply AIP, which stands for assumed in an indirect proof. Now remember, our goal here is to figure out how to construct from this simple proposition not C some sort of contradiction. And it looks like there are a number of potential options here. I could somehow try to figure out how to get D to contradict in this. I might try to see if I can get A's to contradict. Or I might actually just try to get the letter C to contradict. If I can pull one of these C's as an affirmative out, I already have that done. And in fact, it's going to turn out that this is probably the best option simply because there really aren't much in the way of negatives to work with in the rest of the original argument there. So having this negation, all I would need to do is come up with some way to establish an affirmative claim of C. So again, it's not always easy to figure out where you should be heading with this. And the first steps often end up just being trial and error. Now notice I have not C to work with, and line 1 has C that could very clearly be worked into the claim not D by way of the rule of modus tollens. So if I take line 1 and put it together with line 4, I can now conclude that not D must be the case. And of course, modus tollens is going to come into play again here with line 3, which says if A is true, then D is true. And if you put that together with line 5, not D, we can now conclude that not A must be the case. Now, the rather obvious next move is to deal with this disjunctive statement. And given that one of the disjuncts is simply A, line 6 here that we established using the rule of modus tollens, not A, is going to allow us to use a disjunctive syllogism. And from this, of course, we can conclude that both B and C must be true. Now, given that line 7 is a conjunction, B and C, we can, of course, just tear this apart at will and separate B by itself or C by itself using the rule of simplification. But it's pretty clear B does no work for us here. It's not going to help us at all, so we can toss that option out. And of course, at this point, then, we can now say that C must be true using simplification. And of course, at this point, we're pretty much right where we need to be. We have both C and not C asserted in this proof. And so we can put these together using the rules of conjunction, lines 4 and line 8, to get the claim both C and not C are true. And of course, this is absurd. You can't have both of these things be true at the same time. And so this leads us to the contradiction we're looking for. And of course, the point here is very clear. What this accomplishes for us is that we've now shown that the claim not C does in fact lead us to an absurd conclusion. Step by step, using valid arguments all the way, it seems to suggest something that simply can't be true. And that in turn means we can reject the claim. The original assumption here, not C, has to be false. And of course, what we do then is simply say the claim not C is not true by throwing in the double negative there. And then we find from lines 4 through 9, we have now established line 10 is true using an indirect proof. And again, this is now settled. We know that this has to be the case. The last step, of course, is to simply convert this double negative, the not C, into an affirmative claim, which is simply C. And of course, that is the conclusion of this argument. And so we've now shown that this is in fact a valid argument. Now, there's one last point to be made about this, and that is that the methods of an indirect proof and conditional proofs can both be used together in a proof. Just like we saw in the last video where you could take a conditional proof and embed it with another second conditional proof, what we find is you can use these two interchangeably. I can have an indirect proof that is going to use in its proof a conditional proof as a secondary proof, or vice versa. I can have a conditional proof where I start with, and then I use a second indirect proof as a kind of embedded proof within that original conditional proof. So let me give you an example of how this would work. The example is fairly complicated, so it'll take a while to get through, but the idea is fairly simple in the end. So this particular example of an argument has a single premise, which is just a conditional statement. It says, if it is not the case that P and not Q is true, then it's either P or it's R. And the conclusion that we draw from this is, if P is true, then either Q or R must be true. And so the first step is to simply set up the proof like we always do. In this case, we're going to have to cram this way to the top because there'll be many, many steps to get to the end. And so in this case, we have in the conclusion a nice conditional statement, and that suggests at least that we might start by trying a conditional proof. And so if we do that, what we find is I want to take the antecedent of that conditional statement and assume that in the next line, which is line 2 here. And of course, I want to indent this, and I want to basically list as my justification ACP, which means simply assumed conditional proof. Now remember what my goal is in a conditional proof. I'm essentially trying to construct or build a conditional statement out of this. I have the antecedent assumed, P, and of course notice the consequent that I'm aiming at, that I'm going to have to put together in the end, is either Q or R. So somewhere down the line, I have to work from P and this original first premise to construct step by step by step that particular claim, Q or R, so that I can put those together into a conditional statement. If P, then Q and R. And so rather clearly, we're left with a pretty difficult task here. I need to figure out how the heck I can get from just the statement P to the statement Q or R, and there is no clear, obvious path here. So one reasonable suggestion here is to try an indirect proof. Now notice in constructing a second proof here, an indirect proof embedded in this conditional proof, my goal is to figure out if I can show Q or R, and using the indirect proof, what I do is I start by negating that to see if it will produce an absurdity. And so on line 3 here, once again indented, what I get is it's not the case that it's Q or R. So when I list my justification, of course, what I want to do is simply say assumed here in an indirect proof, and I'm going to just abbreviate that with AIP. So now I have this negated disjunction in line 3, and a very reasonable first step here is to turn to De Morgan's law. So I can take that disjunction and convert it to a conjunction by simply distributing out the negations. In line 4 now I have not Q and not R, and that's useful because when I have a conjunction, I can start to pull out the individual pieces. And if you look at line 1 at the top, what I find is that those pieces are going to have to somehow end up separated so that I can use different rules in order to drive different conclusions. So line 4 here, using De Morgan's law, gives us not Q and not R. So this conjunction lends itself to the rule of simplification because I can simply now tear out these individual pieces, not Q and not R, and place them by themselves as an individual assertion. And so at this point, we might ask, which of the two should we aim at? And it doesn't hurt to see what the implications or use of each might actually be. So if we start poking around a bit and we look at the term not R by itself, it's clearly going to play a role in some sense because what we have in the original premise we're working with is this nice conditional statement, if P then R. And of course, not R is going to allow me to use the rule of modus tollens to derive the claim not P. The problem at this point is that conditional statement is not open or available to me because it is currently stuck inside of a disjunctive claim. And so I can't really assume it's true. There's no way to just pull that out unless I end up using the rule of a disjunctive syllogism. Now, not Q, of course, exists also in that same premise as part of a conjunction, which that entire conjunction, being negated, is one of our disjuncts in that statement. So in some sense, what I'm going to need to do is find a way to make the positive assertion that it's P and not Q. Now, given that in our conditional proof, we are assuming P is true, pulling out not Q is going to do some work for us because I can simply put those together into P and not Q using our rule of conjunction. So the reasonable next step on line 5 is to get not Q, which is derived from line 4 by the rule of simplification. And of course, that allows me to put together P from line 2 with not Q from line 5 using the rule of conjunction. Now notice, technically speaking, the disjunct in premise 1 at the very top there that we're working on is it is not the case that it is P and not Q. So simply saying P and not Q is not good enough. What I have to do is negate that statement to make a disjunctive syllogism. And so the next step is to take P and not Q and double negate it using the rule of double negation. Now, having done this, we can take line 7 and then line 1, and using the rule of a disjunctive syllogism, now draw the conclusion that if P is true, then R is true. Now remember what our goal here is in the indirect proof part of this. So lines 3 down. What we're aiming at is trying to figure out how I can get the statement on line 3, it is not the case that it is Q or R, to present us with some sort of contradiction. And so in this case, I can probably best work with R as a way of creating this contradiction. And so if I look at line 8 here, if P then R, which we just established, I can go to line 2 now, and I can derive the conclusion that R must be true using the rule of modus ponens. And now, frankly, I can solve for this pretty easily by going back to 4, where we originally pulled out not Q, and now I can just pull out the other side, not R, using the rule of simplification. And of course, in this proof, we've now shown that R is true, and line 9, and then line 10, we've shown that not R is true. And so we can use the rule of conjunction to put these together to get essentially a contradictory statement. Now remember what this shows us. From line 3 all the way down to line 11, what we're constructing here is an indirect proof. And the basic assumption here is the negation of that particular statement, Q or R. And if that leads us to an absurdity, then that allows us to conclude that this negation simply cannot be true. And so I can now conclude, based on lines 3 through 11 using an indirect proof, that it is not the case that not Q or R is true. And so I can now discharge that statement from the indirect proof. Now keep in mind, I've discharged it from it so I can now use it, but I've only discharged it into a conditional proof. And so I still have to get that conditional proof to resolve itself into something before I have an actual proof. Now, of course, what we're aiming at here is not the double negation of Q or R, but instead Q or R, since that is the consequent of that original conditional statement. And so I need to basically eliminate those double negatives. And of course, at this point, now I'm dealing with the conditional proof. In line 2, I assume in a conditional proof that P is true, the antecedent of the original claim up there, the if-then statement. And then using this indirect proof, I've now shown that the consequent Q or R must be true. And so I can simply put these together. If P is true, then either Q or R is true. And so our conditional proof does in fact lead to the conclusion we're aiming at using lines 2 all the way down through 13, a good chunk of which is actually just an indirect proof. So having fully discharged this conditional statement from our conditional proof, lines 2 through 13, I am now in a position to say that I have a solid proof that this conclusion follows necessarily from those premises, or to put it in very simple terms, this is a valid argument. So that's pretty much an into it. This is what you need to know at its core about indirect proofs and conditional proofs. And really at this point, all there's left for us to do is simply practice constructing various proofs using these methods over and over again until it becomes easier. This is not particularly easy stuff. There's a lot of things going on there. The more you practice, the simpler it becomes. So I'd suggest practicing as much as possible.